Let's define a flownet. A flownet is a graphical solution of Laplace's equation in 2 dimensions. The derivation of Laplace's equation for 2-dimensional flow is covered in most soil mechanics textbooks. The results have a number of important implications for how we actually draw a flownet. Looking at the trajectory of a water molecule, x and y are the directions of flow, as shown, and h is the head at any point. Laplace's equation has many applications in engineering. It represents the energy loss through any resistive medium, for example, electron flow in heated metals, or in our case, the steady-state flow of water through a pervious soil. In geotechnical engineering, flownets are very useful in solving seepage problems, such as estimating seepage losses through an earthen dam, or calculating the uplift pressures under concrete dams, or the water pressures acting on either side of a sheet pile wall. Flownets can also be used to check for instability and erosion at locations where the hydraulic gradient approaches its critical value. The consequences of missing the latter can be catastrophic. So what causes water to flow? Water flows due to a difference in total head or energy between 2 points. It is important to emphasize that it is the difference in total head and not pressure head that causes the flow. This can be easily demonstrated in the following simple experiment. Consider 2 containers filled with water and connected by a pipe as shown. When the water level is the same in both containers, the elevation head plus the pressure head for the tank on the left is exactly the same as the elevation head plus the pressure head for the tank on the right. That is, the total head in both containers is the same. Therefore, no flow will take place between the tanks, despite the tank on the left having a greater pressure head. If we now raise the water level in the right container as shown, the total heads are no longer equal, and the difference in total head, delta H, causes the water to flow towards the container on the left. Problems will be presented initially based on a homogeneous and isotropic soil with respect to its permeability. That is, the soil is assumed uniform throughout and has the same permeability in all directions. The solution to Laplace's equation for 2-dimensional flow adopts the following assumptions. Darcy's law is valid, the soil is completely saturated, and water is assumed to be incompressible. Any small element of soil examined undergoes no volume change due to flow, and the soil is isotropic and homogeneous. From this, we can determine 2 mathematical functions. One that defines the potential for flow at any point in an aquifer, and the second defines the direction of flow at that point. These seepage functions can be represented graphically by an equipotential line, which represents a line of constant total head, and a flow line, which traces the path of a water molecule travelling through or beneath an obstacle, for example, a concrete dam in this case. By varying the equipotential function a number of times, we obtain a family of equipotential curves, each curve representing a constant total head. A second family of curves, each representing a flow line, can also be drawn, and this combination of curves gives us our flownet. The fundamental condition to be satisfied in a flownet is the intersection between a flow line and an equipotential line must intersect at right angles. This can be shown mathematically. In addition, it is convenient to construct the flownet such that the quantity of flow, delta Q, between adjacent flow lines is the same, and the difference in potential is the same between adjacent equipotentials. Furthermore, flow lines and equipotentials are drawn so that they form curvilinear squares throughout the flownet. Like most things in life, we learn best by doing. So let's do a number of examples that will illustrate how to draw flownets and how they can be used to solve various engineering problems associated with seepage.